In this video, we're going to implement a GDT. Now, GDT is a data structure that is used by Intel x86 processors, and it generally defines the characteristics of various memory areas, which we would call segments. So the way that you look at this is, right now we have this big area of memory to work with. And what we typically want to do is we want to divide it up into different pieces, where each of those pieces has a specified size, as well as access privileges, so like who can access the memory and what they can do with the memory. And that's generally what segmentation is going to help us achieve. Now, it's important to note that this is very specific to x86 processors. In 64-bit mode, we actually don't use this concept of a GDT. We instead typically opt for an idea known as paging. And what you'll see is that when we set up our GDT, we're going to set it up in such a way where we're not really using it. We're just providing it to the processor for it to be able to use for the time being. And then later on, what we'll do is we'll set up paging similar to a 64-bit processor, which is going to allow us to more effectively and more granularly manage memory. So this is mostly just us doing this in order to get things initially set up so that we have something to use before we have paging in place. And that's generally what the GDT is going to do for us. So we talked about size and access privileges. We can discuss this idea of an entry in our GDT. So our GDT is really just like an array. And inside of the array, we have different entries. And each entry describes a section of memory. Now, each section of memory is going to have a very specific format, which I am displaying here from the OS Dev Wiki, which is a great resource for learning more about these different concepts that I discuss in each of my videos. So when we take a look at the structure of each entry, which is this data structure right here, we see a very specific structure. So we have what's called a base and a limit. A base defines the address where the segment begins. And you can see that it's actually divided up into three pieces. We have the first part of the base here, the second part here, and the third part here. Important to note that. We'll come back to that a little bit later. But generally, we can know that the base is divided up into three pieces. When we combine those pieces together, we get a 32-bit value, which represents the address where the segment begins. Now, similarly, we have a limit, which is divided up into two pieces here, we could see. The limit is a 20-bit value, and what it does is it tells us the largest addressable unit of memory. So generally, memory can either be addressed in 1 byte sizes or 4 kilobyte pages. Now, generally, we're going to opt to use 4 kilobyte pages. That's what we're going to be doing. So you'll see that we'll set up our limit to use that 4 kilobyte page mode. Now, in addition to this, we have a few other pieces. We have an access byte and we have flags. The access byte is how we define who and what can be done with memory. So generally, what we define is a few different things. You'll see right down here. The present bit is going to tell us if the memory segment is valid. We will always set this to 1. The DPL is very important. It tells us the privilege level of that segment of memory. And we do this typically using what's known as the ring model. With the ring model, we have different what we call rings. Each of them is given a number, and they define the privilege level of that particular ring. So for instance, ring 0 is called the kernel ring. It's the highest level of privilege. And then all the way on the outer side is ring 3, which is the user application area, which is the lowest privilege. So generally, we can define things as either having kernel privilege or user privilege, and there's a few other levels in the middle with a bit more granularity, but typically we don't use them for modern operating systems. We just use 0 for kernel or 3 for user. And what you'll see is that we'll define up our data based on saying, some memory will be in kernel level and some memory will be in user level. And that helps us avoid situations where user applications can modify kernel memory, which is very ideal. We don't want user applications to tamper with the kernel at all. So we can use this to protect our kernel memory. Now we have a descriptor byte, and all this really does is it says whether something is a system segment or a code or data segment. We're always going to set this for our particular application here. Later on, we'll come back to this and we'll take a look at setting system segments with task state segments, but we don't need that right now. We're just going to set everything to 1 to do either a code or data segment. Now, the executable bit is what defines whether something is really a code segment or a data segment. If it's set to 0, it means that execution is not allowed, meaning that this is a data segment. A data segment contains data. You can't execute it. You can read it. You can potentially write to it, but you cannot execute it. Now, a code segment is sort of the difference from that. The code segment can be executed, but it can't be written to. So it can be read, it can be executed, but it cannot be written. If you think about it, it makes sense, right? You wouldn't want to execute data because that wouldn't make any sense. It would probably crash the system. We also don't want to write to code because that would allow modification of code, which is not really ideal. We don't want to allow that to happen, which is why we typically remove that ability with this sort of setup. We have a direction bit, which is going to define whether or not the memory segment goes upwards or downwards in memory. We're always going to set this to 0 since our memory is always going to grow up. We'll just use that convention generally. We have a read-write bit, which determines if something is readable or writable. So for code segments, what this does is if it's set to 1, we're allowing reads. If it's set to 0, we don't allow reads. So we can have like a no read code section if we wanted to. Write access would never be allowed for a code segment, so no matter what, there's no write access. For data segments, if this is set to 0, write is not allowed. If it's set to 1, write is allowed. Read access is always allowed for data segments. So that's the way that that's generally set up. And then the access bit is generally just something that allows us to determine if that memory segment has been accessed at some point. And typically it's used for situations where, like, if we have a segment that shouldn't be accessed and then it is accessed, we can use this to determine if it was accessed and we could throw some sort of fault based on that. Generally, we don't usually use this too much. So for right now, we're not really going to be too concerned with this access bit. Now, the final thing that we have in this structure here is the set of flags. And the flags generally define a few different things. There's a granularity flag, which is actually how we determine our limit. If it's set to 0, our limit will be in 1 byte blocks. If it's set to 1, it will be in 4 kilobyte blocks. So we're going to set this to 1 to use these 4 kilobyte blocks. We have this DB bit, which if it's set to 0, it defines the segment as 16-bit protected mode. If it's set to 1, it will be 32-bit protected mode. We're in 32-bit, so we're always going to set this to 1. We finally have a long mode flag, where if it's set to 1, the descriptor defines 64-bit code segments, and generally we'll see if it's set to 0, it will be any other type of segment. Right now, we're working in 32-bit, so generally we'll probably set this to 0 for the most part. Okay, so that gives you a bit of an overview of the different descriptors that we do have. So using this, we can define some structures that could represent these different pieces. So let's go ahead and do that. I'm going to create a new file called gdt.h. Inside of gdt.h, what I'm going to do is I'm going to define a structure which is going to represent each entry in my GDT. So I'm going to call it gdt entry struct. And it's going to have a field for every single entry that we just discussed. So that being the base, flags, limit, access byte, base, and limit here. Now, something extremely important is that we need to define this struct the exact same way as the segment descriptor from right to, or from bottom to top, really. So that means the limit has to come first, then this base would come next, and then this base, and then this access, limit, flags, and base. Very important that we follow that exact same structure, because when you think about the way that this is loaded into memory, it gets loaded the exact way that we define it. I didn't do this the first time, and I spent a long time troubleshooting this issue. So very important that you do this. So uint 16 underscore t. I want to make sure the sizes are all consistent as well. So the first thing that we have is the limit. It is 16-bit. And then we have the lower base. So we're going to just define these in the way that where this is like the lower part, this is the middle, and then this is the high part. Because that's generally what it's representing in the binary, right? This is like 0 to 15 in terms of bits. This is 16 to 23, and then 24 to 31. So it's just like the low, mid, and high portion of the base. Now, I'm not actually sure why it divides it up in this particular way, but it generally does. So we need to follow the specification regardless of how it's defined. But I'm not actually sure the exact reason why we divide it up into those different pieces. It may have to do with the fact that it should support 16-bit modes. So in some cases, we might not need all 32 bits. I'm not entirely sure, though. So this gives us all the different pieces that we need, right? And you can see that I've defined these in the exact ordering that it was specified in that struct. So you can see that's the way that we want to define it. One final thing that we will provide is this attribute packed. What this does is it just makes sure that the memory is being defined basically like exactly the way that we've defined it here. It's not going to allocate, more space than required. It's going to keep things very consistent. It looks to me like I've done something here. Just want to make sure I've got two underscores, attribute packed. Okay, looks like that's all good. So we'll go for that. Now there's one other struct that we're going to need, and it's called a pointer struct. And all this really is going to have inside of it is it's going to have the limit associated with our GDT. and it's going to have a base. So it's basically just like a pointer to our GDT. We're going to use this to set the GDT inside of assembly. So you'll see how that generally is done as we continue on here. So I'll attribute this as packed as well. And I just noticed what my problem was here. I didn't have the other bracket. There we go. So now we got everything all set. Now there's going to be two functions here. There's going to be init GDT, which is going to initialize our GDT, and we're going to have another one called set GDT gate, which is just going to define each of my different entries. It's going to have a number for which entry this is in my array of entries, and it's going to take in a value for the base. It's going to take in a value for the limit. It's going to take in a value for access, and it's going to take in a value for the granularity or remaining flags that we have available. Now you'll note that I define the base and limit as 32 bits, even though this is divided up into 3 pieces and this is only 20 bits. The reason why I make this 32 bits is because, of course, I don't have a 20-bit integer, so I can't define the exact size. We'll just have to do some bit manipulation to get this to 20 bits. And similarly here, we're just going to do some bit manipulation to get each of the different pieces out of the low, middle, and high. It's just generally going to be the easiest way for us to work with those structs. So with that defined, let's go over to gdt.c and let's implement our GDT. So we're going to include the gdt.h file, which is the header we just created. And I'm also going to, which I think that's probably all I need right now. I'm going to make reference to this external function called gdt flush. This I'm going to implement in assembly. We'll do that a little bit later once we finish up here. Now there's two structs that we're going to need, of course. We need our gdt entry struct, which I'm going to call gdt entries. This is an array of 5 entries. Generally, we'll have about 5 entries inside of our GDT, and you'll see how we define those in a moment here. And then we'll create a struct of our GDT pointer struct. And again, this is just a pointer to our actual GDT. The init GDT function is going to do the following. It's going to initialize the limit of our pointer, which is going to be defined as the size of our GDT entries. So we're going to do GDT entry struct multiplied by the number of entries minus 1. So basically we're just taking the size of each of these individual structs. We're multiplying it by the size of this array here, which is 5. And then we subtract 1. The subtract 1 is just in order to get it offset to the right amount of memory. So this is the general formula that we would use to get that limit. And then in order to get the actual base of the GDT pointer, we're just going to point directly to the address of GDT entries. So it's pointing directly to this array right here. And then we're going to set our GDT gates. So we're going to make calls to that set GDT gate function. I'm just going to copy the definition from the header just because it's long and I'm being a little bit lazy with that. So that's okay. We'll do this right here. And I'm just going to go ahead and wrap this so it's easier to read. So let's talk about the gates that we're going to set. So there's going to be 5 entries in my GDT table. The first is what's called a null segment. It has all zeros. This is required always. So we need this null segment. It's just all zeros. It's just done by convention. Okay, so that's the first thing I need. The second thing I'm going to define is at index 1 of my GDT entries. It's going to start with a base of 0. The granularity is going to be FFFF, FFFF, so that's 8 Fs, right? This is going to be, the limit, right? So this is the way that I define the limit for this segment. The next thing is the access, which I'll explain here shortly, but it's 9A, and then CF for my flags. This is what I'm going to call the kernel code segment. So this is the segment that represents the kernel code. So let's discuss each of these different attributes. So starting off, the base of this is 0, so it starts at address 0, and this granularity, or this limit, combined with this granularity, is setting up 4 kilobyte paging of the memory itself. So that's what these two pieces are doing together. This 0x9a feels like it kind of comes out of nowhere, but this is just the access permissions. Let me break it down for you. So 9a is going to become 1001, and then it'll be 1010, right? When we take a look at this, we need to take a look at this breakdown of our access bits to understand how this is being set. I'll copy this over, just that way we can read through it this one time and see what this is actually setting up. So first things first, the top bit is the presence bit. Like I said, this defines a valid segment. This should always be set to 1, so that's why we have a 1 at the very front. The DPL is these middle 2 bits right here. Remember that these define the permissions for accessing this particular segment of memory. I'm saying that this should be the kernel segment, and as it says here, 0 is the highest privilege, which is the kernel. That's why these middle 2 bits are 0, because this is the kernel code segment. Now the descriptor is the next thing that we have. If it's set to 1, that means that this is a code or data segment. I'm saying that this is a code segment. Since it's code or data, this has to be set to a 1. So that gives us our 9 at the front. Next up, we have this set here. So the next bit that we have is our execution bit. It's set to 1 because this is a code segment. Okay, that's why this bit is set to 1. The bit for 0 is the direction bit. Remember, we want things to grow upward in memory. That's why we have this set to 0, right? So that's why it's cleared at 0. So that gives us our direction. Next thing is read write, okay? If this is set to 1 for a code segment, it means that read access is allowed. So things can read this memory segment. That's why this is set to a 1. And then the access bit, again, remember, this is just saying if this segment has been accessed, we initialize this to 0 because initially nothing has accessed this yet. And at some point, the CPU may set this to 1 if, something has been accessed from this. And that is how we get to 9A for our access bits, okay? So that should help you understand how we're getting each of these different numbers. Now, we're going to do this a few more times, okay? And I'm actually just going to copy this because the next few times are going to be very, very similar. So we're going to have really a few more entries that are available here. So the next entry is going to be entry number 2. It starts at 0. It has the same limit. The only thing that changes is that this becomes 9.2. This is the kernel data segment. So the reason why this becomes 9.2, if we just think about the last few bits of the binary, right? This would be 0010. The only bit that's actually being set here is the read-write bit, right? Everything else is being set up in the way that you would for data, okay? So that breakdown should be pretty straightforward, I think, based on, what we've discussed so far. This is number 3. Number 3 has 0, and this stays the same. This becomes FA, okay? This stays as CF. This is the user code segment. So this A matches this A because these are both code segments. They have the same sort of setup together. Just really quickly, F would be 1111. The main thing that changed here between 9 and F, so just, sort of like breaking this down, 9 looks something like this, and F looks something like this. The only thing that really changed was these middle 2 bits, right? The reason these middle 2 bits change is because they represent the access level of that memory segment. Remember, 0 represents kernel. In this case, we have 3. 3 represents user applications. So that's why these are set to 1.1, because we're trying to make 3 in those bits, which would be a user application, okay? So that's why that's a user code segment. And then finally, this one would be number 4. This would be F2. Remember, this F is because it's user segment. This 2 is the data segment. So this would be the user data segment. So do you see that we divided things up into kernel code and data and then user code and data? That's the way that we're setting up our GDT, and this is a pretty standard way to do this kind of setup. Now, the last thing we're going to do is we're going to make a call to that external function, which is GDT flush, and we'll implement that momentarily as well. This would just take in a pointer to that GDT pointer. So it's going to take in this information, and it's basically going to point our processor towards this GDT that we're defining. Before we get into that, we of course need to implement our set gates, right? So all this is really going to do is just going to set the GDT entry at the number provided. It's going to set each of its properties as required. So we're going to start off with the base. So base low is going to be defined as the base ANDed with 0xFFFF. So just think about this. This would be the lower set of bits, right? So it's going to take those lower set of bits, it's going to AND with it. That would just give us the lower set of bits. That's the way that this bit mask is going to work. And then, of course, we're going to do a similar thing with base middle and base high. Base middle takes our base, it shifts it by 16, and then it ANDs it with 0xFF. So it does a shift and then just takes those bottom few bits and places them into the middle. And then similarly, we'll see that that works pretty well for our base high, right? So with base high, what we have is we have the base shifted by 24, and we AND that with 0xFF, right? So it's all just bitwise operations, and I would encourage you to try, doing these out on paper and just see how these shifts work, right? Just to make sure that you really understand them, but they're pretty straightforward shift-based operations. Now, the way that we set our limit is going to be as follows. So dot limit is going to be equal to that limit variable, and we're going to AND it with 0xFFFF. The reason why we're doing that is because remember that our limit is split into two pieces, right? So we have these 16 bits right here, and then we have the remaining 4 bits here. So what's happening here is we're getting these 16 bits and setting them. So that's all we're really doing here. That's why we're doing FFFF. We're just doing a bit mask to get those 16 bits and placing them in, okay? Now, where things get a little bit more interesting is in the flags. So with the flags, what we're going to do is we're going to do limit shifted by 16, and we're going to AND that with 0x0f. The reason why we're doing this is because, so note that the flag and limit sit next to each other, right? So each of them takes up, I think, 3 bits of space, right? So what's happening is we're getting this bottom set of limit first, and then we're going to place these flags on top of it. So that's why we're doing this operation. This is the bottom set of the limit. And then what's going to happen here is we're going to set this to flags or equals that granularity variable, and it was 0xf0. Now, this is a really interesting sort of operation, and the main reason why we do this is because when we take a look at these, sorry, I said that these were 3, these are 4 bits, right? So each of these are 4 bits. The reason why we have to do this is because we don't have a 4-bit integer, right? We only have 8 bits. So we define the field as 8 bits, and then we split it in half and place each of them in their corresponding locations. This is some bitwise operations again. If anyone ever asks you, when will I need to use bitwise operations? This is exactly the case where we have, a 4-bit value and we need to split it up inside of an 8-bit integer or something like that. This is where we need those sort of bitwise operations. Now, the final thing that we need to set inside of here is access, and that's an easy one. We just set it equal to it, and we're good. So that's the easiest one out of the bunch. Okay, so we're getting very close here. The last thing that we need to do is we need to implement GDT flush, which is actually a pretty easy operation. We do this in assembly because we need to be able to tell the processor where our GDT table is. So we create a global function GDT flush, and we're going to define GDT flush right here. And what I'm going to start by doing is I'm going to get the value that was passed in as an argument off of the stack. So I'm moving the ESP plus 4 to EAX. That's going to give me this GDT pointer address right here. The way that we tell the processor where our GDT table is with a special instruction called LGDT. LGDT just simply tells the processor, here's the GDT table. That's all there is to it. Now from here, we need to update a few registers. We're going to move into EAX the value 10, and then what I'm going to do is I'm going to move into the DS register AX. And I'm going to do this for a few different registers, and I'll explain exactly what this is doing. So this is DS, this is ES. Oh, ES, this is FS, this is GS, and this one is SS. So what this is doing is each of these registers, like DS, for instance, is a segment register. It defines locations of different segments. So DS is, for instance, the data segment. Each of these represents a segment. And what we're doing is we're pointing it towards our GDT table. This 0x10 is the offset to that GDT. So that's why we use this 10 value here. So we set this inside of each of these segments to tell it where it can find the segments for our GDT table. Now there's one other segment that needs to be set, and that is the code segment. The way that we set that is really interesting. We can't really move a value into the code segment. Instead, what we do is we jump to the code segment like this. This is a bit of a weird operation, but generally all it's doing is it's setting the code segment by way of a far jump. So we're doing a far jump based on the offset here, and that's going to allow us to set the code segment as well. So that might be a little bit odd, but it's just setting each of those segment registers. So at this point, we do have everything up and working. let's go over to our make file here, which I've created just recently. And basically with this make file, I've just created, compiling rules for each of the C files and the NASM files and linkers together for them. I'm just going to add in my values that I've just created. I should really define these flags as a variable, and I'll get around to that at some point as well to make life a little bit easier, but that's okay. So we'll do gdt.c into gdt.o. And then what I'm going to do is I'm going to NASM to set up gdt.s. I call this file gdts.o just to distinguish it from this gdt.o. We'll link those together, gdts.o, and that's all we really need. Okay, that gives us everything. So let's go ahead and try to make this and see if we have any errors, which we might have, right? It does look like we have a few small errors here, so let's just go ahead and get these fixed. We have this sort of implicit cast here, which is causing a little bit of trouble for us. Let me just come over here and just make sure that our types are all lined up. We have our unsigned int base here. And then when I come up here, it's setting it based on the address of GDT entries. And generally, these are just warnings, right? It's just a warning of an implicit conversion. I think that these are probably okay for now. We can fix these problems a little bit later by defining some custom types to work with this. But for now, let's just leave that. We'll be okay with those warnings for the time being. We'll fix them a little bit later. But for now, I think that that's okay, assuming that our code actually does run. And actually, as I'm saying that, I realized that we didn't actually run this code in kernel main. That would be probably helpful to do. So what I'm going to do is I'm going to include our gdt.h, and inside of our gdt.h, what we're going to do is we're going to run that init gdt function, and then I'm just going to print out a message afterwards just to confirm that we made it out of that function okay. Okay, so we'll do our make one more time here. And then I'm going to go ahead and run this in QEMU, and let's see what happens. And as you can see here, we get the output GDT is done. Now, one question you may have is, how would I know if it didn't work? And this I can tell you very easily because I've accidentally made this mistake. So let's say that I defined this in a weird ordering, okay? Let's try to make this fail. Do you notice how my operating system just kind of like goes back to this grub page here? This is, I believe, what's referred to as a triple fault. In this kind of situation, your operating system just crashes. And this is a little bit maybe panic-inducing because it's like, oh no, what has gone wrong? So this sort of thing can be very complicated to deal with. But for now, we'll just end off by saying, okay, we got everything working. Our GDT looks to be working well because it didn't do that kind of fault. So that's okay. And what we'll do is in the next video, I'll actually show you how you can work through and debug your operating system in cases where this sort of thing happens, because this is a really painful process of debugging. I want to help you understand how you could go about debugging that and understanding that sort of process. So with that, we got our GDT up and running. Thanks so much for watching. I'll see you in the next video.